So in this video, we're going to continue our lecture series for physical chemistry at the undergraduate level, and we're going to extend upon some of the laws that we spoke about in our first lecture. So let's talk about the mixtures of gases. This is the mixture of gases. So Dalton's law. He said that the pressure. So Dalton said that the pressure exerted by a mixture, right? So the pressure exerted by a mixture of an ideal gas, and we spoke about the ideal gas equation in the first lecture, right? So the pressure exerted by a mixture of ideal gases is the sum. So we have a sum of pressures exerted by the individual, right? So we have exerted by the individual gases occupying the same volume alone, right? So the pressure exerted by a mixture of ideal gases is a sum of the pressure exerted by the individual gases occupying, right? By the individual gases occupying the same volume. Occupying the same volume alone, right? So let's put this in terms of an equation with respect to Dalton's law. So what we're saying is that P is equal to P1 plus P2 plus P3 plus a sum all the way up to Pn, right? And so if we put on our statistic head, we could actually write this as a summation where the top is n and we go some arbitrary j is equal to 1, and we have the sum of pj, right? So that's how we could simplify Dalton's law with respect to a summation, right? So to continue in what we were saying, okay, well, the pressure exerted by each gas, if it is, right, so if it is occupied the container, right? So the pressure exerted by each gas, if it occupies the container alone, so if it occupies the container alone, we call it the partial pressure. We call it the partial pressure of that gas. We're gonna underline partial pressure. So we call it the partial pressure of that gas. All right. One thing I want to note here is that the gases must, right? So the gases must be mutually unreactive. Right? So the gases must be mutually unreactive for the equation to hold, right? So that is our caveat with Dalton's law, right? So the gases must be mutually unreactive for the equation to hold, right? So in the equation above that we wrote, P1 is the partial pressure, right? So P1 is the partial pressure. P1 is the partial pressure of gas number 1. P2 is the partial pressure of gas number 2. All right, so we're slowly easing into our physical chemistry at this point. And lastly, P3 is the partial pressure of gas number 3. All right, and again, we're speaking about this equation. We're just laying out the foundations. All right, and so you could see that this is pretty much etc. Right, we could go all the way up to 27 if you want. Right, so for a total of n, right, different gases of the mixture. For a total of n different gases in the mixture. Right? So we're saying it's just a summation. Right? So by the ideal gas law, by the ideal gas law, for a container of fixed, right? So the volume is fixed. So for a container of fixed volume V containing these n gases, right? So we're using again n for gases and volume for V, right? We could actually say P1 is equal to N1 times R over T divided by V. Or we could say P2 is equal to N2, where N is the number of moles, times RT over V. Or we could say P3 is equal to N3 times RT over V. And we could go all the way on, etc., etc., etc. Right? Again, just to put some context, we say this is where Nj is, again, the number of moles. Right? So the number of moles of the jth component of the mixture. Right? So we're saying that P1 is equal to N1 times RT over V, and P2, etc., where N is, again, our number of moles. Right? So let's do an example. Let's talk about an example. How would we solve an example? Right? So let's say that we have a 10.0 liter container, right? And it holds exactly 1 mole of N2 and exactly 3 moles of H2, hydrogen gas, at 25 degrees C. Right? The question is, what is the total pressure in the vessel? So this is a question that we want to answer. What is the total number of pressure within that vessel? Well, let's solve the problem first. From Dalton's law, we know that P is equal to Pn2 plus Ph2. Right? It's a summation of the partial pressures. Now, if we using the ideal gas, using the ideal gas law for each, gaseous component of the mixture, right, we could actually split it up, right? So we could actually say, okay, well, Pn2 is equal to N2 times RT over V. And we can also say that Ph2 is equal to NH2 times RT over V. Now, remember when we deal with the ideal gas equation, we must have our temperature in Kelvin. So in this case, T is equal to 25 plus 273.15, and that is equivalent to about 298.15 kelvins. Right? Now, they've given us our volume of the container, so the volume is equal to the volume of the container, and that is equal to roughly 10.0 liters. Now, they have given us the moles of each, so they told us that N2 is equal to 1.00000 exactly, and NH2 is equal to 3.00000 exactly. Right? So these are just numbers that are given within our question above, right? And we know that R for the ideal gas constant is about 0.08206 liters, atmospheres, Kelvin, inverse, mole, inverse. So plugging it in for each equation, for Pn2, this is equal to approximately 1.000, and that's our number of moles, times 0.08206 times 298.15, and that's our T, and this is all divided by V, which is our 10.0 liters, and that's equivalent to around 2.45 atmospheres. We could also do the same thing for pH2, and this in this case will be 3.000, right? Because that is the number of moles of hydrogen gas, and this will be equal to 0.08, the ideal gas constant, times 298.15, right? All divided by the volume again, which is 10.0 liters, and this is equivalent to about 7.35 atm. So therefore, the total pressure P is equal to 2.45 that we calculated for nitrogen gas plus 7.35 that we calculated for hydrogen gas, and this is equal to about 9.80 atmospheres, roughly. So that's an example of how we'd calculate the total pressure using Dalton's law. Now let's switch gears from that to mole fractions. Let's talk about mole fractions. Let's talk about mole fractions and partial pressures. So the mole fraction, and let's underline this because this is our topic. We're going to denote it as X with a small j, right? So the mole fraction of each component, J in the mixture, right? So in a mixture, so I'm going to say in a mixture, is given by the moles. It's given by the moles, right? So it's given by the moles of J. So it's given by the moles of J molecules n lowercase j, right? So that's the number of molecules divided by the total, so divided by the total number of moles of all the molecules in the mixture. In the mixture N. So we say that the mole fraction of each component, so we say the mole fraction of x lowercase j of each component j in a mixture is given by the moles of j molecules, and j divided by the total number of moles of all the molecules in mixture n. So what do I mean? Well, let's look at the equation. We say that xj is equivalent to nj divided by the total number of moles n. So this is our mole fraction formula. Now, one thing we want to keep in point here is that xj is a dimensionless quantity, so there's no dimensions to it. So it's a dimensionless quantity. Right? So to define our equation again, we say that xj is equal to nj over n, all right, where nj is equal to the number of moles of component j, or I should say lower j, so of component j, and n is equal to the total number of moles for all the components. Right? So again, nj is equal to total number of moles for the j component, whereas n in our denominator is equal to the total number of moles for all components. So that's how we define the mole fraction. Now remember that no molecules of component j in a mixture is actually equal to 0, right? So none of the components in xj is equal to 0. So that's a critical point that we need to make. We also need to make sure that we know that pure components j, so pure components j, not a mixture, is xj, which is equal to 1. So the pure components, which is not in a mixture, xj is equal to 1. So let's talk about for n components, right? So for an n component, for an n component mixture, we could actually write a formula: n1 plus n2 plus n3 plus etc. go all the way up to plus nn. We could write it as a summation like we did earlier. So this is a summation of where j is equal to 1 of n and j, and that is equal to n. So this is our broken down formula to summarize our partial or mole fraction. Now we could actually do something interestingly. If we divide, so if we divide the above equation, which is what we have here, right? If we divide it, the above equation through by n, so if we divide the above equation through by n, this is actually what we get. We get x1 plus x2 plus x3 plus go all the way up to xn is equal to the summation of where j is equal to 1, we have n, where we have xj is equal to 1. So it's a nifty little trick that we did right there. Now, to summarize the equation, we could say then the partial pressure of component j can now be defined, and this is the meat of the problem, can now be defined using the mole fraction can now be defined using the mole fraction as Pj, right? So Pj is equal to Xj times P. And we could write this out as N, so we could write this out as Nj over N times nRT over V, and that's equivalent to NJRT over V. So that's our mole fraction equation, right? So then we could actually say that the sum of the partial pressures, in a mixture equals the total pressure, right? So that's a very important point. So sum of the partial pressure in a mixture equals the total pressure. And how would we do this in some sort of equation? Well, we know that P1 plus P2 plus P3 plus all the way up to Pn is equal to X1 times P plus X2 times P, where X is our mole fraction, plus X3 times P. And this goes all the way up. This goes all the way up to Xn times P, which is equal to X1 plus X2 plus X3, all the way up to Xn. Move over here a little bit. All the way up to Xn times P, and that is equal to P, the total pressure. So all I did was just factor out my x's. So that is equal to the mole fraction, since then the sum of all the mole fractions equal to 1, right? So this is important. The sum of all the mole fractions must equal 1. So let's talk about a real gas. Let's switch topics from our mole fraction component to what we call a real gas. And a real gas is also what we call non-ideal gas. So this is in the real world, right? So real world gas or non-ideal gas. So let's talk about it. So the first thing we need to know is that for all real gases, they actually show deviations. They show deviations from the ideal. They show deviations from the ideal gas law, especially at high pressures. Right? So all the real gases show deviations from the ideal gas law, especially at high pressures and actually low temperatures. Right? Now these deviations from ideality are best studied by measuring the compressibility factor. We're going to talk about the compressibility factor. Right? So these deviations are best studied by measuring what we call the compressibility factor. Right? So we'll say again, the real gases disobey the ideal gas law at high pressures and low temperatures. So how do we define this in a mathematical formula? Z is equivalent to PV over nRT. Now, Z here is actually dimensionless, right? It's a dimensionless quantity, so we need to define that. It's a dimensionless quantity. Now, let's look at the difference. For an ideal gas, Z is equal to PV over nRT, which is equal to 1, right, at all pressures and temperatures. At all pressures and temperatures, right? For real gas, however, Z is equal to PV over nRT, where this does not equal to 1 at all pressures. Well, not at all pressures, my mistake, but at high pressures and low temperatures, right? So this would be at high pressures and low temperatures. So that is the difference. Now let's look at a graph of what we're talking about. Let's look at, so we're going to talk about a plot. We're going to talk about a plot showing deviations from ideality at about 0 degrees for 3. So we're going to talk about for three different gases. We're going to show it below. All right. Again, one of the things that we note before drawing this curve is that Z for a given gas can be greater, right? Can be greater or even lesser, right? Or lesser or less than 1, right? So let's talk about the curve that we are actually talking about. How do we differentiate an ideal gas from a real gas? So on the x-axis we have pressure in atmospheres. This is about 0. This is about 200. This is about 400. And this right here is about 600. And we have Z on our y-axis. In the midline, we have Z is equal to 1, Z is equal to 0 at the bottom, and we have Z is equal to 2 at the top. And so what we can see, and maybe I should represent these in different colors, right? Here is hydrogen gas. And you can see that as Z increases, the pressure increases. Now, here is ammonia gas. And we're going to represent methane, CH4, as and then increases simultaneously. Now, I wanted to make a correction to myself. This blue line, the blue line should be going down in this respect, right? So this is ammonia, and this would be what we call, obviously, a real gas, right? So the blue line going across is not the ammonia, but rather the blue line going down. So that's a correction on my part. Now let's switch gear and let's talk about what we call the virial equation. So the Virial equation says that Z is equal to PV over nRT, which is equal to 1 plus some arbitrary number B times T times P plus C times T times P squared, and we're going to expand this a little bit, plus some arbitrary number D times T times P to the third power, and you can see the pattern, etc. Right? So this is what we call the virial equation. So this is called a virial. This is called a virial equation, or in other words, a virial expansion. And for context, B times T is called the second virial coefficient. So B times T is called that second virial coefficient, and you could guess what C times T is called. C times T is the third virial coefficient. And obviously D times T you would expect to be the fourth virial coefficient. Now, what are some of the factors that we need to know about the virial equation as physical chemists? We know that it represents an empirical approach. All right, so the virial equation represents an empirical approach to account for real gas behavior. We also know that virial coefficients vary from gas to gas. And we know that the virial coefficients also vary temperature. We also know that at low pressure, the virial equation actually reduces to the ideal gas law. Right, so at low pressures, the virial equation reduces to the ideal gas law. Right, this, and we spoke about the equation of state in our previous lecture. This is a type of equation of state. Right, and we need to know that the magnitude of the virial coefficient decreases as the power of P increases. Alright, so we need to know that the magnitude of the coefficients actually decreases as P increases. So let's revisit Boyle law. The boil temperature for a gas is when B times T is 0. Right? So the boil temperature for a gas is when B times T, like we spoke about, is actually 0. So let's look at the boil temperature on a graph. Here we have P on the x-axis, we have Z at 1 in the midline, right? And we have Z at 2 at the top and 0 on the bottom. For high temperature, right, for high temperature, we see something like this. This would be high temp. Whereas for low temp, graph actually looks something like this. And this would be low T. Whereas for the boils temp, look at it. BT is equal to 0. And this is what we define as the boils temperature. So again, some words on the graph. Same gas at 3 different temp. So we're looking at the same gas at 3 different temperature. We also see that there's minimum deviation. So we have minimum deviation from ideality at low pressure. And we also see that there's also little deviation from ideality at the boil temp. Right, so we have little deviation from ideality at boil temperature, so at the boil temperature over a wide range of pressures. Right? So these are my comments on the graph that we have above. Now let's transition to what we call the critical point, and you may have seen this in your General Chemistry 2 lectures, but we're going to talk about the critical point. How does a critical point look on a graph? Let's graph it. Here we have a graph of P versus V. Pressure on the y-axis, V on the x-axis. Here's our graph. And so we have various points. We could say that this is A, right? We could say that this is point B. We could say that this is point C. We could say that this is D. We could say that this is point E. And we could say that this is F. And at this point, we have liquid, whereas this point we have gas. Right? So let's talk about what these points mean. Point A, let me write in my white. Right? Point A is the gas Boyle's law actually obey. Right? So this is where PV is equal to a constant. Right? So that is point A. Now point B is where the gas, we have serious deviations. This is where we have serious deviations from Boyle's law. So in other words, we would say that PV does not equal to a constant, right? So in this case, we would say that PV does not equal to a constant. So that is at point B. How about C? Point C, we have a gas plus droplets. So we have gas plus droplets of liquid, right? So this is where we have gas plus droplets of liquid. In this case, we would say that P is equal to a constant as V decreases. So that would be point C on our curve. How about point D? Point D is where we would have gas plus point D is where we'd have gas plus liquid. And in this case, P is still equal to a constant as V decreases. Point E, this is where we have no gas left, right? So I can't show the curve above, but again, point E, going back and looking at the curve, is where we essentially have no gas left. In this case, it's only liquid. Right? So it's very hard to compress the liquid further. Point F, it's all liquid, like we mentioned above in our graph. So point F, it is all liquid. And in fact, any reduction in volume V actually requires enormous increase in pressure. In other words, the steep slope of the curve. Right? So let's look at two different curves. We have pressure on the y-axis and volume on the x-axis. If you look at curve 1, right, and these are several little points right here. Versus curve 2, notice the difference in the shapes of the curve. Here, the PV isotherm at T2 is, again, T2 is greater than T1. Where here, the PV isotherm at TC, or some arbitrary constant TC, is where TC is greater than T2. Right? So some comments on the two graphs that we have just drawn above. At T greater than or equal to some arbitrary constant TC, there's no liquid. So no liquid gas interface actually appears throughout the compression. Right? So in other words, the gas is converted smoothly to a fluid without a phase transition. Whereas the temperature above, so the temperature above which the gas liquid conversion cannot be made is what we really is matter of really why we're talking about these whole graphs, and that is called a critical point. Right? So it cannot be made is called the critical point. And that is TC. So TC is what we call the critical point. Now, some last points before we end the lecture, right? The pressure at which the gas fluid conversion so the pressure at which the gas fluid conversion occurs is actually called the critical pressure. PC. Right? And the corresponding molar volume is called VC. Now, the dense fluid phase that form the critical point is actually called a supercritical fluid, right? So the dense fluid phase that forms above the critical point, TC, is actually called a supercritical fluid. Right? Now, last thing before we end the lecture is that the supercritical fluid or supercritical fluid extraction, SFE, right, is actually an important industrial technique. So the supercritical fluid extraction, SFE, is an important industrial technique. For example, decaffeinating coffee. Right? So you can decaffeinate coffee with supercritical CO2. So that's it for the lecture, and I'll see you around for lecture number 3.